Thank you, all of you, for coming today. And again, I'm honored to be here. So today, I'd like to tell you about the origin of gold in the universe. By the way, have you ever thought about this question? Where does gold come from? Probably some of you now have gold, maybe in ring, in necklace. Probably some of you do not have it. But when the universe, our universe started, such element didn't exist in the universe. But now we know there's a gold. And this is very much related to the topic in astronomy, because in the universe, some phenomena has created gold. And now we know there's a gold. And the origin of the gold is actually very much related to the topic of Nobel Prize this year. Probably some of you know the Nobel Prize in Physics this year was awarded for the first observations of gravitational waves. Can I ask a question? Have you ever heard gravitational waves? If you have heard, please raise your hand. Professor, yes, of course. Okay, thank you so much. Maybe about half. So that looks quite different, the gravitational waves, Nobel Prize, and gold. But today, I'd like to tell you these are closely related to each other. And this is an exciting topic in astronomy, astrophysics research area. So today, I'd like to talk about 3 topics. First of all, I'd like to briefly introduce what is gravitational waves. By the way, Professor Chen kindly annotated some Chinese characters for you to grab some meaning. Actually, I am Japanese. I can also read Chinese character. And the first topic is about gravitational waves. And the second topic is why gravitational waves and gold are related. That's not clear at all. Then finally, I'd like to tell our recent research to hunt for gravitational wave sources. And I will roughly talk for 1 hour or so, but probably it's too long for you. So if you have any question, please feel free to ask at any time in English or in Chinese, then someone should translate. And probably I can understand some. So gravitational wave has a word of gravity. What is gravity? So now all of you are sitting in the chair. So you must feel gravity. So you are now attracted by the Earth. So this is gravity. So if you jump, you fall down. So this is gravity. So we are now here, and we are attracted by the Earth. The same is true for example, rocket. Rocket cannot go straight because there is a gravity by the Earth. Then this orbit changes because of the force toward the Earth. I think many of you know this concept. But to understand gravitational wave, probably it's better to understand gravity in this way. So when some heavy mass exists, then the space-time looks like this. It's distorted. Let's think about this way, in this way. Then the gravity can be understood like this. So we are falling down to the distorted part. This is towards the center of the Earth. And again, the rocket cannot go through because this is falling into this distortion. So gravity can be also understood as a distortion of space-time. Then, what is gravitational wave? So if such object is moving very fast speed, then this distortion of space-time propagates. So this is something we call gravitational wave. And in the universe, we have some object with extremely strong gravity. And if such object is moving with extremely high speed, then such object emit gravitational waves. So this is a concept of gravitational wave. And to have gravitational wave, we need object with extremely strong gravity. Now you know I'm reading Chinese character, right? Object with very strong gravity. Sorry, I cannot understand this. Emit gravitational waves. So this is the topic of my presentation today. We want to study this kind of phenomena in the universe. But to have such a gravitational waves, we need object, astronomical object with extremely strong gravity. But astronomers know how to make such object. And to make such object, we need relatively massive star, more massive than our sun, probably by factor of 10 times heavier than the sun. And we know such massive stars finally explode in the universe. This is called supernova. After supernova, objects with strong gravities are made. And there are two kinds of such extreme objects in the universe. One is neutron star, and the other is black hole. Have you ever heard black hole? Yes, black hole. Thank you. How about neutron star? Yeah, for some reason, this is less popular. This is much more popular. But today, of course, I will talk both topics, but the main player is actually neutron star. This is extremely interesting object in the universe. So this is just a brief overview how to make such object. But inside of the stars, what's happening? So probably some of you have heard that our sun is shining because of the nuclear reaction. So inside of the star, hydrogen is converted to helium, and this produces energy. So this is a reason why our sun is so bright, so luminous, because huge amount of energy is released by this nuclear reaction. But as you can imagine, if you do not have hydrogen anymore in the star, then we cannot have such reaction. Star or sun is keeping its shape by producing energy from the center, and that's balanced with their own gravity. So to have a star in that shape, we need nuclear reaction. So if all the hydrogen is used, and if there is no hydrogen anymore in the center, then next, helium is converted to carbon or oxygen. But this continues for heavier and heavier elements. I'm sorry that display is a bit distorted, but please assume this is almost circle because our sun is not so distorted. So in this way, heavier elements are synthesized or produced inside of the star. So that's something astronomers know from a long time ago. But when iron is produced in the center of the star, then such star collapses into the center. So let's assume huge star collapses into the center. Then you can create extremely compact, extremely small star. And this is the birthplace of the neutron star or black hole. So neutron stars or black hole are formed inside of the star when they collapse into the center. By the way, when they are formed, we know the outer material surrounding this compact star finally ejected into the interstellar space, into the space. And this is so-called supernova or supernova explosion. So star actually explode. So when we observe the sky, we can identify supernova. We can observe supernova, and this is one of the examples. So when star explode, then the material is ejected into the space, and it is observed like this. So this is an actual supernova that is observed. If you zoom in the center, actually we can also find neutron star here. By the way, this image is created by combining visible light and X-ray. And X-ray is shown in blue color, and visible light is in yellow. So this is a normal star. Maybe we can go back. So we have many stars here. But only this point looks blue because this object is not normal star, but emitting X-ray. And this is very special in neutron star. And this is a reason why we know this is actually neutron star. So neutron star is an object formed inside of the star and remains after the explosion of the star. So this is a key player today. So let me explain what is neutron star. So neutron star has a mass mass is similar to that of the sun, or probably slightly heavier than the sun. This is about 500,000 times heavier than the Earth. So this is a heavy object. But in the universe, this is not extremely heavy object. But what is special of neutron star is its size. The radius of the neutron star is only about 10 kilometers. I tried to measure 10 kilometers in the map of Taipei. I think this is about 10 kilometers. So let's assume our sun is so big and compressed into the size of Taipei. then you can make neutron star. So this is a such dense, such compact object. So the star with only 10 kilometers exists in the universe. So you can roughly calculate the density, mass in 1 cubic centimeter. This is the density. Then that's, this is a billion ton. I think the character of this is the same, right? Yeah. So 1 billion ton. So if you take small piece from neutron star, then that has a weight of 1 billion ton. So that's extremely dense object. And that extremely dense object and that extremely strong gravity. So probably you have heard that if the gravity of the Earth is assumed to be 1, then the gravity of at the surface of the moon is only 1/6. So if you jump on the moon, you can jump higher than in the Earth. I can easily calculate the same number for the neutron star. And this is about 200 billion. So that's extremely strong gravity. Extremely strong gravity. And if such object moves around, then such object can emit strong gravitational wave. So this is the reason why neutron star is important and interesting for gravitational wave. I also talk about the black hole because black hole can be also formed inside of the star, but black hole is black hole. Actually, I have black dots here. It's not visible. That's good, because that's not visible. And this is extremely strong. This black hole also has an extremely strong gravity. So even the light cannot escape from this black hole. In this sense, we cannot see the black hole. So neutron star and black holes are objects in the universe with extremely strong gravity. Probably some of you have heard that many stars in the universe forms binary or has a companion. So if such twin of stars exist in the universe, then one star can explode as a supernova and forms neutron star or a black hole, and the second star do the same. Then this can finally merge with each other, and this emits gravitational waves. And we know this kind of phenomena is actually happening in the universe. So I have just talked about what is gravitational waves and what kind of objects produce the gravitational waves. And the key players are neutron star and black hole. And if such extreme objects merge with each other, then it moves with quite high speed. Then it emits gravitational waves. So this is about the first part. So probably you know what kind of gravitational wave sources can be expected in the universe. Then the second topic is why gravitational waves are related to gold. That sounds nothing to do with each other. But I'd like to convince you that these are closely related. And when the universe started, there are not many elements in the universe. Our universe started with hydrogen, helium, and small amount of lithium. But now we know there are many elements. So now if you breathe, you absorb nitrogen and oxygen. Without oxygen, you cannot survive. Your body is made from, of course, water, H2O, carbon, oxygen, calcium, and so on. I'm sure this building has a lot of iron. But such element didn't exist in the universe at the beginning. And this is a periodic table of the elements. And hydrogen and helium is here. But there are so many different elements. So I just marked some famous elements. So this is hydrogen, helium here, carbon, oxygen, calcium must be here, and iron. But now we know these elements are formed inside of the star. As I said, inside of the star, nuclear reaction is happening, and heavy elements are produced. So these are surely made inside of the star. But today's topic is, for example, gold or platinum. They are heavier than iron. So they are not easily produced inside of the star. And still, no one really knows where these elements come from. So the title of this talk is not written here, but exploring the origin of the gold in the universe. Honestly speaking, I don't know the answer. And that often happens in the frontier of research, because research is an activity to solve the mystery. So there's always a mystery, and this is a kind of a easy example. So we do not know the origin of the gold, or what kind of phenomena made such elements in the universe. And still we do not know the answer. We try to understand the origin of such elements. And I think we have some hint quite recently, so I will tell that story soon. To produce the element heavier than iron, we need neutron. Creating new element or heavy element means adding proton. If the number of proton increases, then that is different element. But iron already has 26 protons. So it's not easy to put proton anymore, because this has a plus charge and this is a 26 plus charge. So it's not easy to put proton. So we need neutron instead. Neutron we can easily attach neutron. But that's not a new element, because number of neutron doesn't matter for the element. It's called isotope. But if you put too many neutrons, then this such nucleon decays by radioactivity. And in this way, heavy elements can be produced. So to produce elements heavier than iron, we need lots of neutrons. That's why neutron is a key player. The question is where such neutron is available in the universe. Because if neutron is alone, that's easily changed into proton. So it's not easy to find a neutron in the universe. But now we know neutron star merging neutron star is a really good place to have many neutrons. So several years ago, the astronomers and the physicists in the world performed a computer simulation of merging neutron star. So let's assume this is one neutron star sliced, and this is the other neutron star. Then we can solve the physical equation in the computer and simulate what happens when neutron stars merge with each other. So this is a movie. So let's see. So when two neutron stars merge, then actually that's really violent phenomena. So you may have seen that it's not quiet at all, but some material is ejected into the outer world. Because this is from a neutron star, there are lots of neutrons. So we can calculate what kind of elements are included inside of such ejected material. And we found gold is here. Correctly speaking, this is not only gold, but many, many elements heavier than iron can be formed in the ejected material from neutron star mergers. That's really exciting. But this is computer simulation. So we still do not know whether this really happened in our universe. So we have to confirm if it's really happening. So I myself performed a numerical simulation again and found that neutron star merger can be visible in the visible light by producing elements such as gold and platinum. The reason for that is radioactivity. So when you make heavy elements by putting so many neutrons, then such element decays by radioactivity. And by radioactivity, there's energy. And by using that energy, such objects should be visible for our eyes. So this is our numerical simulation. So this means if we can find such object on the sky, we can say heavy elements are produced in the neutron star merger actually. So this can be tested by astronomical observations. Then the question is how to find such object, how to find a neutron star merger. Probably we are just observe, or we can just monitor entire sky, but that's too difficult. But now we know how to find neutron star merger, and that is gravitational waves. So the idea is following. When gravitational waves are observed, then astronomers look for that position to have such emission, such light. Then we can test if heavy elements are produced in the neutron star merger. So that's exciting collaboration between gravitational waves and the normal astronomy or electromagnetic astronomy. So now I think I could convince you that I want to hunt for gravitational wave sources. I want to find out gravitational wave sources because that can be gold maker. So finally, I will tell you the current situation or recent research topics about the hunt for the gravitational wave sources. So in the world, there are 3 gravitational wave telescopes nowadays, currently. And in US, there is a project called Advanced LIGO. They have 2 detectors. And in Europe, there is an Advanced Virgo. And in Japan, now we are constructing Kagura. But now 2 detectors in US and 1 detector in Europe are working. And the target is, of course, neutron star mergers and black hole mergers. Let me briefly explain the mechanism to detect the gravitational waves. So you can see 2 straight lines. Actually, this has a 4 kilometer, 4 kilometer, 4 kilometer. And what is inside is something like this. So launching the beam and split into 2 arms. So this is 4 kilometer and 4 kilometer. And this comes back by reflected by being reflected by mirrors. Then we can detect the returning beam. And by using the interferometry technique, we can accurately monitor if this length changes or not. So we can keep monitoring if this length is constant or not. And when gravitational waves pass to gravitational wave detectors, then this mirror or this length should change a little bit. So by this way, we can detect gravitational waves. But this is an extremely tiny signal. So the fraction of the length changed by gravitational waves is something like this. Let's assume 1 meter length, my arm. If gravitational waves pass to my arm, then 1 meter changes by 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 minus 21. So number of 0 is 21. But if such a small change happens in this detector, then actually this detector can detect such a tiny difference. So this is more or less a more professional plot, but this is a figure shows the sensitivity or performance. And please forget about this x-axis. But roughly speaking, this is a noise, and this is minus 21. How tiny it is. The distance to the sun from the Earth is 100 million kilometers. 100 million kilometers. So if gravitational waves comes into this way, then 10 to minus 21 correspond to the size of one atom. So if our sun comes toward us by size of one atom, then gravitational wave detectors can detect such tiny difference. Let's surprise. That's amazing. Probably many of you know Orion and the Betelgeuse. This is a red star, bright red star. The distance to the Betelgeuse from us is about 600 light year. So 10 to minus 21 means Betelgeuse come to us by 1 centimeter. Such tiny difference. So 10 to minus 21 is such tiny difference. So probably you cannot believe that, but such a signal is actually observed in 2 years ago. So this is the data from Gravitational Wave Telescope. Probably 2 years ago, or about 1 year and a half ago, many newspapers should broadcast this. But please carefully read this axis. So this says 10 to minus 21. So this is extremely tiny signal that is detected by the modern gravitational wave telescopes. So that's really big achievement, and this was caused by the merger of 2 black holes. Maybe I can skip this. So I think this is a really great achievement, and this is the reason why this year's Nobel Prize was awarded for the observation of gravitational waves, so, gravitational waves for the first time 2 years ago. So our motivation to hunt for gravitational wave sources is exploring the origin of gold in the universe. And so far, 4 detections have been made for black hole merging black hole. And this, thanks to this achievement, Nobel Prize was awarded in this year. I mostly talk about a neutron star merger. And we believe this produces gold or platinum or heavy element, and finally shine. So if we can find gravitational waves from this event, and if we can find such object in visible light, then we can study the origin of element in the universe. And actually, I prepared this slide about 1 month ago. And at that time, I was going to finish with this slide, no detection yet about a neutron star merger. But this August, finally, the first detection of gravitational waves from neutron star mergers has been made. This happened in this summer. And this was announced in this Monday, on this Monday. This is just by chance, actually. So I decided our schedule already several months ago, and this just happened this month, this Monday. So I'm quite happy to tell about this latest story. So actually, this summary slide is not correct anymore. So now we have 1 detection of neutron star merger. And of course, many astronomers looked for this object. And people found light. So this is an image taken with Japanese Subaru telescope. So this is a really first observation of light, or visible light, from gravitational wave source. And this is a distant galaxy, many stars. And this object was not present before the gravitational waves, and suddenly appeared. So I think this is a signature of heavy element production, heavier than iron. So probably we observed the place of heavy element production, such as gold or platinum. But this is still the first example. There's only the first case, only 1 case. let me emphasize that there's a great contribution from Taiwan, and Professor Chen, Professor Ip did a press conference this Tuesday, I think. So this is extremely recent news. And they also observed that object, and they studied the population, population of stars in the galaxy. So many people, not only Japanese group, but also Taiwanese group, people in US, people in Europe, so people all over the world, researchers all over the world are now actively working on this topic. And probably we have, at least we have observed one case. But this is really the beginning of new astronomy. New, I mean, the collaboration with gravitational waves and electromagnetic wave. Electromagnetic waves include visible light, for example. So this is really the first step of this new astronomy. And it's really exciting to think about the future, for example. So we have to answer many questions. For example, how much heavy element do neutron star merger eject? And what kind of elements are actually produced? And how often such object, such merger occurs in the universe? And by answering these questions in the future, we hope we can understand the origin of the gold in the universe. And as I said from the beginning, we still do not know the clear answer about the origin of the gold in the universe. But I think we started a very nice first step. And I think the future is exciting, and I hope you stay tuned. So I finished my talk, and thank you so much for your attention.